in the homework. So we have this beam shown here with a length of 20 feet with two different loads. We're being asked to find um, the sample space for the bending moment at point A. The sample space is just the all the possible outcomes in terms of values for the bending moment, which is the load times the distance, depending on what point each of the loads has been applied to. So what we can do is we can create a table where the first outcome is if the loads are not applied anywhere. You can see the bending moment is 0. And then we again create all the different combinations, and we end up with some values for MA. And that's really the sample space. So it's a discrete sample space. And then the second question was asking about the having these three events that are already defined, which cover a range of values. But remember, a range of values, because it's discrete, it can only take a certain set of values. So we can count the different outcomes. Are the events E1 and E2 mutually exclusive? Mutually exclusive means that they cannot ever happen together. So let's see, E1 and E2, we've got MA being greater than 5,000, E2 is between 1,000 and 12,000, and we already see that there are some values, like this one here, 7,000, where they both can happen at the same time, therefore they're not mutually exclusive. For the third part of the problem, we would have to assume some probabilities for each load being applied to a certain point, and if the positions of W1 and W2 are statistically independent, we should find the probabilities associated with each of the possible values. Now, for that one, what we can do is essentially take all the possible outcomes, or the combination of those, and because they're statistically independent, we can essentially use their intersection, so if both of them are happening together, and in order to calculate the probability, we just have to multiply the probability. So let's start with an easy one, so this one here, for instance. So if we have C load being applied in both positions, we've got a bending moment of 14,000, and we have a 0.6 probability for W1C, and then multiply that by 0.5, which is the W2 at C. Now, things get a little bit more complicated if we have the event of not being applied to any of the points for specific loads. So, for example, this one here, let's look at this one here. We've got B load applied to W1, so we've got a 0.25 probability, and then we need to make sure that the W2 is not being applied anywhere. And in this case, the probability of not being applied anywhere, we have 0.3 of being applied at B, 0.5 of being applied at C. So we take the complement of that, which means that the load is not being applied anywhere. We multiply that by the probability of W1 at B, and we end up with 0.05. And the last part of this problem was calculating the probabilities of the following events. So if we, let's see if we can scroll here. There we go. So we've got the probability of E1, and remember that E1 is these events values here, 1, 2, 3, 4, 5 different values. So each of those has a probability associated with it, right? Because it corresponds to a combination of applying the loads at the different points. So what we can do, because they're mutually exclusive, for example, this combination can never happen at the same time as this one, right? Because you've got W1 at B, and then W2 not being applied can never happen at the same time as W1 being applied at nowhere, and then W2 not being applied anywhere. So that means that we can just add the probabilities. So essentially we have the union for all these events here. So For PMA greater than 5,000, we've got 2, 4, 5 probability, so 2, 4, 5, and so forth. I guess the only difference might be when we have the intersection of V1 and V2. And in this case, we can find out the rows where both of them are happening. So we've got 1, 2, 3. And we got these 3 values here. And for the complement of V2, we can either do 1 minus PE2 or what you see 0.545, so that would be easier, but we can also do it because again we have too few outcomes and values. We can also do it here. Alright, moving on to problem 2, where we have probabilities of fuel cell technology and solar energy being commercially viable with some probabilities, 0.7 and 0.85. First question is, what is the probability that there will be energy supplied by these alternative sources in the next 15 years? Now, the way I read this question, I'm thinking about both of these sources providing energy. Some of you actually thought it was the union, which is understandable to a degree, and therefore, I only took 1 point from that question. But pretty much you know what to do. If it's a union addition rule, if it's an intersection, we essentially knowing that they're statistically independent, we can just multiply the probabilities and get 0.7 times 0.85, get a probability for that event. Now the second question is, what is the probability that only one of these sources will be commercially viable? And in that case, we do have a union of 2 events, or a combination of 2 events. The first one is that fuel cells and not solar energy, and the other one is solar energy but not fuel cells. And again, these events are mutually exclusive. They can never happen at the same time, which means that their union here actually becomes the sum of the 2 probabilities. Since these intersections are statistically independent, we can just multiply P of F and then the complement of S, and the same thing for the second term, and we know everything and we get 0.36. Now, for the third problem, where we have a building failing due to excessive settlement or by collapse of the superstructure. So those are the 2 failure modes. The probability of excessive settlement is 10%, probability of superstructure collapse is 5%. And then if there's excessive settlement of the foundation, which again always means a conditional probability, the probability of the superstructure collapse is increased to 0.2. First question is, what is the probability that building failure will occur over its life? So let's define the event C for the collapse of the superstructure, E for excessive settlement, and F for the building failure. Now, building failure can occur if either C or E occurs. So we're given that information in the first sentence here. So we've got the union of C and E being the probability of failure. And we have the union, we can use the addition rule, so we have PC plus PE minus their intersection. Now the intersection here, we have an additional piece of information, which is the conditional probability of already having excessive settlement and then getting the probability of the collapse. So we can express this intersection here as the conditional of C given E, which we know is 20%, and then we've got the probability of E. Now we know all these terms, and we're able to calculate the probability of failure at 13%. Second question, if building failure does occur, what is the probability that both failure modes will occur? Again, conditional probability, you see the if there. And we have both the failure modes, so excessive settlement and collapse of the superstructure, given that failure occurred. Now, this one we can express, we can replace F, and you'll see why, with the union that we calculated right above. And now with this conditional probability, we can use a definition, which is the intersection over the probability in the conditional here, so F. But instead of F, we just write it as the union of E and C. So here we've got the intersection of E and C, and then we have the intersection of that with the union. Now, when we look at this, we know that E and C need to happen, and this one here says that E or C or both could happen. So think about this. We've got E and C definitely happening, and E or C or both happening. So this event here translates to just the intersection. So we could have distributed these, but it would get pretty complicated. So anytime you see something that can turn into something very complicated, draw your Venn diagram, as I've said many times, or think about what this combination of events actually means. So we're by having an intersection here, we can again use the conditional like in question A to calculate that. We've already calculated the probability of failure as 13%. We know everything. We get 0.154. And the last part, the probability that only one of the two failure modes will occur over the life of the building. That means that we have a combination of two events similar to problem 2. So we got the intersection of E complement C, E complement, and C. So these are mutually exclusive. So again, we can do the same thing as we did in problem 2b. So we just have the sum. And then we can think of this as, again, we can draw a Venn diagram or just think about the intersection of E with C complement is essentially E minus the intersection with C. So let's just do that here real quick. So we've got, let's say this is E, and then we've got event C here. So if we're looking for E intersection with C complement, essentially we're looking at, this is E, and C complement is everything outside of C. So in essence, we end up with just this area here. So it's probability of E minus the probability of their intersection. So that's the first term here, and then the second term we can do the same thing. So we know everything, put in the numbers, and we get a probability of 11%. And that's it for homework 1.